Earthquakes as triggers of volcanic eruptions. Volcanoes and earthquakes are two of the most dramatic expressions of the dynamic processes operating beneath the Earth's surface. While they are distinct phenomena, their roots lie in the movement of tectonic plates and the activity of Earth's crust and mantle. Volcanic eruptions involve the expulsion of molten rock, magma, gases, and ash from beneath the crust, whereas earthquakes are the result of the sudden release of accumulated strain energy along faults. The interaction between these two hazards has long fascinated geoscientists. One of the most intriguing questions is, can earthquakes trigger volcanic eruptions? The answer is yes, under certain conditions. Earthquakes can act as catalysts, disturbing magma systems and pushing them toward eruption. This article explores in detail how earthquakes can trigger volcanic eruptions, the mechanisms involved, historical case studies, and the implications for hazard assessment. Tectonic setting, the shared roots of earthquakes and volcanoes. To understand the connection, it is essential to recognize the tectonic environment. Most volcanoes and earthquakes occur in similar geodynamic settings. 1. Subduction zones. Plates converge, with one descending beneath the other. Melting of the subducted slab produces magma that fuels volcanic arcs, Japan, Indonesia. Strong megathrust earthquakes often occur in the same regions. 2. Rift zones and divergent boundaries. Plates pull apart, creating fissures. Magma ascends easily through fractures, forming volcanoes, East African Rift, Iceland. Earthquakes accompany the stretching and faulting of the crust. 3. Transform boundaries and hotspots. Even in areas without direct subduction or rifting, volcanic systems, like Hawaii, and strike-slip faults, like the San Andreas, coexist, though interactions are less frequent. Thus, volcanoes and earthquakes share spatial and tectonic proximity, making interactions likely. Mechanisms by which earthquakes trigger volcanic eruptions. Earthquakes do not create magma, rather, they act as triggers when a volcano is already in a critical state. The following mechanisms explain how. 1. Fracturing and creation of pathways. Earthquakes generate stress and crack the crust. These fractures may connect magma chambers to the surface. Even if magma was previously trapped, new conduits can enable rapid ascent. Large quakes are particularly effective at creating networks of fractures extending kilometers deep. 2. Stress transfer and pressure redistribution. Seismic waves can change the stress regime around a volcano. Compressional or extensional stress alters the balance of forces on magma chambers. Even a small shift in pressure can destabilize a magma system that is already near critical thresholds. 3. Resonance and fluid mobilization. Seismic waves can resonate with fluids, magma, water, or gas, inside volcanic plumbing systems. The shaking may mobilize bubbles in magma, decreasing density and increasing buoyancy. This allows magma to rise more easily. 4. Hydrothermal system disturbances. Many volcanoes are capped by hydrothermal systems, where water circulates under pressure. Earthquakes can disrupt these systems, suddenly reducing pressure. A drop in pressure allows dissolved gases in magma to exhale violently, leading to explosive eruptions. 5. Gas exhalution and volatile release. Magma contains dissolved gases, CO, SO, HO. Earthquake shaking can cause nucleation of bubbles, much like shaking a soda bottle. The sudden release of gases drives magma expansion and eruption. Conditions necessary for earthquake-triggered eruptions. Not all earthquakes near volcanoes lead to eruptions. Key conditions include 1. Magma chamber pressurization. If the chamber is nearly full and overpressurized, small disturbances may push it past the eruption threshold. If it is empty or poorly charged, even a large quake may have no effect. 2. Proximity and magnitude of earthquake. Large quakes, magnitude more than 6, within tens of kilometers, are more likely to trigger eruptions. However, even distant megaquakes can affect volcanic systems by transferring stress. 3. Pre-existing structural weaknesses. Faults, fractures, and cracks enhance the ability of seismic shaking to mobilize magma. Volcanoes with brittle, fractured crust are more vulnerable. 4. Type of volcano and magma. Gas-rich, viscous magmas, andesitic to rhyolitic, are more explosive and easily destabilized. Basaltic volcanoes, with more fluid magma, may experience lava outpourings instead. Historical case studies. 1. Mount Fuji, Japan, 1707 Hoi eruption. Triggered by the magnitude 8.6 Hoi earthquake. Within weeks, Fuji erupted, covering Edo, Tokyo, with ash. A clear example of tectonic stress transfer leading to eruption. 2. Mount Pinatubo, Philippines, 1991. A series of earthquakes preceded the cataclysmic eruption. Crustal fractures opened pathways for magma ascent. Seismic activity and magma intrusion worked hand in hand. 3. Eyjafjallajökull, Iceland, 2010. Earthquake swarms occurred for months before the eruption. The quakes reflected magma forcing its way upward. Seismicity served as both a precursor and a trigger. 4. Chile's Cordon-Col, 1960. The largest recorded earthquake, magnitude 9.5, occurred in southern Chile. Within days, volcanic eruptions were reported along the Andes. Demonstrated how giant earthquakes can destabilize volcanic arcs. Scientific studies and evidence. Statistical correlations. Studies show that volcanic eruptions are more likely in the months following large nearby earthquakes. However, the relationship is probabilistic, not deterministic. Laboratory experiments. Simulations of magma under seismic shaking confirm that vibrations promote gas bubble formation, increasing eruption potential. Numerical modeling. Models of stress transfer demonstrate how even slight changes can critically destabilize magma chambers. Monitoring and forecasting. The interaction between earthquakes and volcanoes highlights the importance of integrated monitoring. 1. Seismic monitoring detects both tectonic earthquakes and volcanic tremors. Earthquake swarms often precede eruptions. 2. Ground deformation. GPS and INSAR measure crustal movement, revealing magma migration. Earthquakes followed by uplift are a warning sign. 3. Gas emissions. Sudden increases in SO or CO can indicate pressure changes after an earthquake. 4. Hydrothermal activity. Changes in hot springs, geysers, and fumaroles provide additional clues. Implications for hazard assessment. Understanding earthquake-volcano interactions is crucial for risk management. Early warning. After major earthquakes near volcanic arcs, authorities should increase volcanic surveillance. Disaster preparedness. Communities near volcanoes should be aware that earthquakes may signal increased eruption risk. Infrastructure protection. Cascading hazards, earthquake followed by eruption, pose compounded threats to infrastructure and human safety. Challenges and uncertainties. Not all earthquakes near volcanoes trigger eruptions, making prediction difficult. Some eruptions occur without any earthquake trigger. Distinguishing between coincidental timing and causal relationships remains a scientific challenge. Researchers emphasize that while earthquakes can trigger eruptions, the underlying state of the volcanic system is the decisive factor. Conclusion. Earthquakes and volcanic eruptions are interconnected natural phenomena driven by tectonic processes. An earthquake can trigger a volcanic eruption if the conditions inside a volcano are already primed, particularly if magma chambers are pressurized and structural weaknesses exist. Mechanisms include fracturing of rock, stress transfer, resonance, hydrothermal disturbances, and gas exhaustion. Historical case studies, from Mount Fuji in 1707 to Pinatubo in 1991 and beyond, demonstrate that earthquakes have indeed triggered eruptions. Yet the relationship is not universal. Many quakes occur near volcanoes without consequence. Thus, earthquakes are best understood as triggers, not causes. Integrated monitoring that combines seismic, geodetic, and geochemical data offers the best chance of anticipating such events. For communities in tectonically active regions, awareness of this connection enhances preparedness for cascading hazards. Ultimately, studying how earthquakes trigger volcanic eruptions deepens our understanding of Earth's dynamic systems and helps mitigate risks posed by these twin natural hazards.